the final countdown today. Try to wrap everything up into one burrito and see if we can put it down. What do I want to say? I do want to point out again, final projects due when? Saturday nights, yes. Very good. And everything else, too, for that matter. There is one last assignment next week. It's a short video assignment to round out the course. The workshop is done after this week. Creativity projects, get those in this weekend, too. And yeah, if you've done everything, if you're missing any video assignments, go back and do them. Send me links to them. And no reason for anybody to fail this class. That would be crazy. What else I want to say? There's these evaluations that are going around too. Make sure you do your course evaluations. Please, give feedback on the assignments, different things about the class in general. Don't say that you hate lecture courses or something like that. That isn't going to change in the future. But anything that you can tell me to make the class better for next year will be useful. It also obviously goes to my bosses, so don't be too mean to me. Hopefully, if you've hated something you've told me before now, that would be useful earlier. So anyways, do those. Otherwise, I think that's all the business that I had to get to. I am going to try to talk about the present situation with cosmology being in the hands of physicists in opposition to cosmology being in the hands of mythologists today. And I want to kind of weave a story about how that came to be and what the future looks like today. And I think that's a good way to wrap everything up. Before we get there, though, I want to make sure that we understand everything from the last class, because we've done both big legs of the Big Bang cosmology, which is our standard physical cosmology today. I want to make sure everybody understands that. And I have one thing I want to review concerning the question Levin asked at the end of class. I want to make sure that we really understand what's going on with that figure. And yeah, Anastasia and I spent a long time on the phone with Pierre-Marie making sure that we understood that figure really well. And actually, we had learned a couple of things, so I want to clarify those. But first, last chance for any participation points. If anybody wants to help us get started in a little discussion of what's come before, as far as yesterday especially. I want to make sure the Big Bang cosmology is understood very, very well before moving on. Yeah?
We talked a lot about the discovery of the microwave background and the controversy of it.
Indeed. Yes, and I'm going to definitely get back to that. I want to talk a little bit more about the ocean hypothesis. Yeah.
You also briefly talked about how the Big Bang theory is outdated, or you think, or there is evidence that it is not exactly correct.
Yeah, I think everybody realizes there's some problems with it. And so the question becomes whether, it's replaced outright or whether it's modified. It seems like the timelines need to be revised in some sense, mainly due to these super mature-looking galaxies at the beginning of time. Jasmine.
Doesn't the day before the birth of the galaxy keep on getting pushed back every time we get a more advanced telescope?
Yeah, that's part of the situation, right? So at some point the question becomes, will we just keep pushing it back forever? There's something, I hope you guys have picked up on this. It's been kind of hard for me to convey this to you because a lot of this history concerns arguments that no longer take place in the modern attention space. But for most of the history of modern astronomy, so in let's say the 20th century, people were squarely divided between this kind of steady-state eternal cosmology and this Big Bang cosmology. And the Big Bangers declared victory after the discovery of the microwave background radiation. And the leading steady-state cosmologists who also accepted the, let's say, Doppler interpretation of the distant redshifts, they surrendered because they didn't have an explanation for the CMB. which is why it's so important that we are 100% sure that that CMB is actually A, cosmic, and B, that it has something to do with the beginning of the universe, both of which I've raised some questions about that I think are pretty important to answer at least. So, yeah, there's a question going forward, you know, will we revitalize the dialogue between the eternal steady state cosmologies and the Big Bang cosmologies, or will it always, are we going to be stuck in this era of just pushing the date of the universe back every time we build a big telescope? It's an interesting question. I don't know the answer to it. Yeah, in the back. Remind me your name again. I always forget. Antonio. Yeah, okay.
Yeah. In relation to like your question, do you think that the Big Bang is still like the best explanation, or like are you leaning towards like another thing like the Big Bounce, or like what do you think is the most logical?
Well, I love that you use the word logical, because I think that they're all quite logical. All of these theories are logical. And I'm not sure if you were here when we were talking about this, but logic is really just this if-then reasoning, where you basically say, here's my assumptions about the situation, and if these are true, then blah, blah, blah. So I think they're all quite logical. It's just a matter of, in some sense, metaphysical assumptions, like, do you accept that in conditions outside of the Earth, let's say in far, far away places, can physics break down? If you're comfortable with that, then it's logical that you come up with all sorts of things from black holes to Big Bang singularities and everything else. If you're just metaphysically, on principle, uncomfortable with the idea that physics can break down sometimes, then none of that logic follows for you. So you ask, you know, my preferred cosmology, I suppose. You know, does anybody, you guys probably, some other people who have been here every class probably are sort of, you guys can probably peg me for my cosmology preferences. It doesn't really matter what I like, to be honest with you. I just want you guys to be aware there's some different options here. I suppose I'm in the camp of people who think that physics doesn't break down ever. And so I'm deeply uncomfortable with any cosmology that follows from, well, physics was different at some point in time, or some place in the universe, physics is just different. I don't see any reason to believe that on principle. But it is a very popular interpretation. And, you know, to back that up, the very popular philosophy that governs a lot of the physics landscape today is a philosophy that has its roots in positivism, which basically says that humans are not smart enough to comprehend everything that's happening. And I don't buy that for a second either. I find that to be a pretty disempowering philosophy. So, you know, that's where I stand. But it's not that I'm right. That's just my opinion. You know, it's just what I'm comfortable with. I know plenty of brilliant people who have different metaphysical assumptions that go into the way they look at the universe. And certainly there's plenty of smart people that think, you know, the quantum world is nonsensical and that's perfectly reasonable. It's just a matter of preferences at the end of the day, which one you're comfortable with. I don't know, what are you comfortable with, Antonio? Yeah.
I'm Christian, so I guess if that answers your question.
Well, not necessarily. That can mean many, many, many different things.
I guess I'm the opposite.
Right on. So it's like if your metaphysical baseline is that the universe needs a birthday, period. Like if that's the only way that you can comprehend reality, that's totally fine. I mean, but of course, you're going to come down on a completely different side of the equation than somebody who doesn't feel that primal necessity. And I understand it too. Like, obviously, everything comes and goes. All bodies are eventually destroyed and recycled. Things in and of themselves seem to have birthdays and expiration dates. So I totally get why people would like to assign that same principle to the universe itself. Yeah, there's not really a right and wrong. That's the funny thing. I mean, the question really does become, though, first of all, can that ever be physically proven or shown, right? So the Big Bang cosmologists try to say, well, there's evidence for this creation moment, right? I personally find their evidence extremely weak, and I've tried to make that case because your textbook does a bang-up job of defending that evidence. So there are two sides to this story. I've tried to provide in the lectures. This is why I wanted you guys. This is why I make attendance worth anything in this class. I need you guys to be here to hear a different perspective, because you're not going to hear this perspective in the textbook, right? Generally speaking, when paradigms shift, it takes a while for the paradigm to catch up to the textbook, something like that. And usually the people who are advancing the paradigm shifts are somewhat heretical. In the past, they've been burned at the stake for their ideas. Today, they might just be driven out of research by lack of being able to get funding, for instance. So, I don't know. I'm presenting these ideas to you just because I really want you guys to see science is always the kind of war of ideas, right? And everybody is quite logical. So, at the end of the day, it comes down to evaluating assumptions. Does this assumption make sense or not? Is it valid to assume X, Y, and Z? And the history of science would show that whenever a paradigm is overturned, it's because the assumptions are found to be invalid that underpin the theory in the first place. It's never the logic. It's never the processing. It's never that people are doing completely irrational logics. So that's kind of interesting. You mentioned you were a Christian too. I think that's really interesting, and I'm going to talk about that a little bit today too, because what's kind of funny is that, there's two ways to look at any religious text, right? There's let's say a physicalist interpretation of it, where you're like, or a literalist interpretation of it, and there's a more mythological approach to it, right? Where you can look at the stories in a foundational text like the Bible and try to extract the deep allegorical meaning of them, right? And so I'm going to try to look at, not necessarily the Christian Bible today, but I'm going to look at the Babylonian version of that, maybe because it's a little less charged, because nobody in here is a Babylonian, so we're not going to offend anybody. But I want to show you how perhaps there's a lot of wisdom encoded in that cosmology that isn't physical in nature. And what's really bizarre about the moment that we live in right now is that our cosmology is entirely physical, right? The physicists are in charge of cosmology, and that's a really weird situation with no precedent, from what I can tell. So, I don't know. I think these are really interesting points that you're raising. Who else has thoughts, concerns? Yes?
I found it very interesting how, when we were talking about the Big Bang Theory, what's the main theory and how it works, that there's light without atoms. It starts with the light, expansion. I just find that really weird, because we're always taught atoms are the foundation of everything, but light's first.
I mean, this is a great example too, because this is an assumption. You can make, even a really brilliant scientist can assume that there might be light without atoms. That's an assumption. I don't know how to talk someone out of that assumption, except to say we've never seen that. I could say that's never been demonstrated in a laboratory. Every time that we look at light in the laboratory, there's always an emitter and an absorber, 100% of the cases. But if you say, well, again, under extreme circumstances, say at the hypothetical beginning of the universe, it was possible. It's a very difficult thing to argue against, right? I mean, I don't actually even know how to have a disagreement with somebody about that, because all I can really say is, well, we've never seen that. I don't know. And I have a hard time, I guess, putting my faith into things that don't match what we've seen in the laboratory. But it's not always the case. And light itself is so poorly understood. It's kind of crazy. All of this talk about black body radiation in this course, people studied that stuff 150 years ago, and they just kind of moved on. And, it's very bizarre how poorly something as absolutely foundational as light, how very poorly understood it is in terms of what it actually is. Not how it proceeds, not the mathematical equations that govern its behavior, but literally, what is the atom doing to the other atom during light, right? Is it just shooting a magic bullet, or is there some sort of weird physical handshake happening? I would, of course, lean on the more mechanistic side of that, but somebody else might be totally comfortable with magic bowling balls of energy. Yeah. So, one second. I think Levin had his hand up first.
It's like, how can we ever see light without an observer?
Yeah, it's a good question. So it has to be an assumption, right? You have to assume that it is possible or that it isn't. I don't know. And I don't know how to argue against it otherwise either.
In the world of like magical cosmology, creativity, I've been trying to come up with ways we could actually just be inside of something huge that's living, like our universe is actually just like a quantum level inside of something massive. And then I came across like biphoton emission, which I don't understand very well. I'm gonna do a terrible job trying to explain, but something about how like there's little bits of light inside of us that just kind of spark.
Oh, biophotons. Yeah.
Biphoton emission. And then I checked to see if, suns do that, and it said, nah, not really. So that's
I mean, that's actually a really, you're not alone. So I would say the most interesting people in science to me today in biology are really interested in the biophoton question. Certainly light does interact with material inside of your body. Like you can take, for a long time people like to ignore the role of light on non-plant-based systems, right? But you can just take a flashlight and like hold it up to your cheek and see that light is penetrating into your body, basically, even visible light, right? So, and we know that light has effects on molecules and so forth. They're all very light sensitive, even not just your photoreceptors in your eyes, but all of your molecules, especially mitochondrial molecules, are sensitive to the chemical changes that are going to happen when you interact with light. So that's a huge area of interest. Another really interesting area of interest is what you just said, which is, I don't think it's been given like the proper terminology right now. What you're talking about, the conscious universe, the idea of stars being somehow biological in some sense. It often gets swept into the bin of something called panpsychism, which is this idea that everything is animate in some sense. We're just not looking on the right timescale. So this table is animate. Everything has some degree of animacy. That's a pretty extreme position that I have a harder time with. But when I look at something like stars and galaxies with incredible, wildly complex electromagnetic networks going on, it's hard to at least not open my mind to the possibility that they have the infrastructure to do everything that a brain is doing, right? So that's a really far-out-sounding idea, but I'm seeing it entertained by pretty serious scientists these days too. So yeah, that's a frontier. I often, I think I've made this case in this class before too, that I could totally imagine another planet like ours, somewhere far, far away, where instead of cosmology being handed over to physicists, it was handed over to the biologists instead, who looked at something like the galactic rotation and said, oh, well, it's an organism and it's moving because it wants to be moving that way. And now we need to figure out the mechanism by which it signals the different parts of its body how to move and so forth. So, yeah, it seems a little bit arbitrary to me. But, yeah, we have the physicists in charge for some reason. And I think in some sense that's because we're in love with math. We're really impressed by math. Most of us don't understand math, especially high-level math, like second-order differential equations. And when people start whipping that stuff out, a lot of people surrender and run away. So I think the physicists, in some sense, have kind of browbeat everybody off of the playing field. But I can tell you, as someone who's studied high-level math, that it's sourly disappointing when you actually understand what people are talking about. It's not that profound. It's just detailed. And math, of course, was the best way to describe motion dynamics prior to computer animation. Nowadays, anybody use Blender in here? Heck yeah. Free 3D animation software. Blender is a much better way to describe how physical systems interact with each other, right? You can show a movie of how something's happening. You don't need second-order differential equations, right? people didn't have that at the outset of physics. And so very high order complex mathematics became the standard for describing how physical systems interacted. So again, a weird sort of holdover from history of how these things were developed. But yeah, we live in a world where mathematics and mathematical physics in general has dominated the landscape of cosmology, and it doesn't even seem to be a particularly physical version of mathematical physics, right? It's perfectly comfortable with wildly fantastical interpretations of mathematics. You know, you reach an infinity or a singularity in your math equation, and instead of saying, well, our equation probably stops working at this, you know, density of stellar mass or something, they say, oh, great, we'll make an we imagine an ultra compact form of matter that we've never seen before, or we imagine a black hole, which is a rip in the universe, and physics breaks down and all this stuff, right? I mean, in my opinion, that's kind of what happens when you let mathematicians stop doing math and start doing physics, which they never really cared about in the first place. They're good at doing quantitative manipulation and analysis. They're not much for the real world and for interactions of physical objects. So it's kind of what happens. So, you know, got to be careful who you turn over the keys to the castle to. You're kind of going to get what you deserve in some sense. Is that too harsh? Maybe that's too harsh. I'm sorry. I love math too, though. I just, again, I make the case to you guys. Math is fantastic at describing patterns, right? It's really good at generalizing patterns. You know what it's terrible at? Explaining anything. It doesn't ever explain anything. Like you can put an equation on the board, and we can all stare at it until we, you know, the cows come home. But without somebody coming over and saying, this variable means this variable means that, this constant exists to qualify this, without explaining the math, without actually explaining what's happening in the physical system, the math is meaningless. It's just a bunch of quantitative adverbs. You can't even make a sentence out of it. So we get really confused. Math is amazing. It allows us to parameterize our systems, build incredible, you know, technologies, incredible rockets, all this cool stuff. It's great. Math's a really cool tool. But it's not the same as science. And it's not the same as an explanation for what's actually happening. And it's very easy to get seduced by it and think that your description of a pattern is the same as an explanation, when it actually is nothing like that. So it's kind of interesting. What else? What other thoughts we got? Yeah, Diane.
Last lecture, we talk about math and Planck. And I was interested at the waves. When we talk about the waves, we talk about the bomb waves. That would be like throw the bombs and then they will make like a ring on it.
Oh, the nuclear explosions. Yeah.
And the ring will be all black. And that's because of the match up with the water.
Yeah, that's worth. Do you guys remember when I briefly showed a slide of a nuclear explosion test, and I was explaining to you. There's this black ring that travels out actually, and the reason that I showed that to you is I wanted to show you that water can behave like a black body in the optical range if it's compressed, basically. So the nuclear tests proved this, and my point is that if water can behave optically black in this compression, then we should certainly believe that under less compression that black body peak is going to be shifted out of the visible range. It's going to be weaker, but there should still be a black body signature to water. And I'm going to unpack that before we get rocking here in a second, because the figure that I tried to explain to you guys about the ocean temperatures and so forth was a little bit confusing. So I'm going to come back to that in a second. But the reason that I showed that nuclear test was just to prove to you guys that water can definitely behave like an ideal black body. And the reason we know that for sure is because when you shock load it, it becomes visibly black, actually, in the visible range. So the peak of the black body shifts under compression into the visible range. That's why I showed that. The reason we talked about the WMAP and the Planck satellites is that the Planck and WMAP satellites are often used to justify the fact that we've measured the cosmic microwave background radiation far away from Earth. It's measured at L2. The reason I talked about them was to say, hey, wait a second, these are not actually direct measurements of the CMB. Both of these experiments assume the value of the CMB and the spectrum from the earlier satellite missions that are in low Earth orbit and on Earth, and then they take those and they look for either differential measurements of that, or they look comparing it to an onboard probe that they calibrate to that COBE measurement, which is the low Earth satellite. So the WMAP and the Planck satellites did not actually measure the CMB. They measure the difference in that same look. When they have that signal in mind, they filter for it and they look for the difference in both directions, which is different than actually measuring the source itself. And it's very bizarre because you would think that if we're going to build our cosmology, our entire worldview about this universe on this Big Bang thing, and the CMB is at least 50% of that argument, that we would want to be really sure that there actually is a cosmic source of it in the first place. And I don't think that that's been proven. I don't even think it's a good argument, especially considering how tight that data is when it's close to Earth and how noisy it is when it's far away from Earth, even using the differential stuff. I mean, there's almost no laboratory experiments where you would get such tight error bars on a measurement. And the black body spectrum of the CMB as measured in low Earth orbit is impeccable. It's incredibly tight, actually. It seems like you're measuring something right next to you, basically, which is really, really bizarre to me. Good question, though. All right. What else? Anybody? Oh, okay.
Getting Nobel Prizes for things that like aren't fully true now or like appropriate for the situation. I just thought it was interesting that they have those. Because it's kind of funny how like, now that we look back on it, it's like, oh, that's not completely true.
Yeah, I actually, I don't know. I feel, I'm very torn about the Nobel Prize thing, right? Because it's this huge, I mean, it's literally a king knights you with it, basically, right? Like this king puts this ribbon on you. It's in, where is it, in Switzerland or Sweden or it's in Norway? I can't even remember. It's in one of these Scandinavian countries. There's a king involved, a huge ceremony, big cash prizes given. And then, of course, once you're a Nobel Prize winner, you're basically a god in the scientific community. Which, like, in some sense, seems like a cool incentive to drive people towards discovery. But yeah, it creates this huge problem where it's like, it assumes that science moves forward in these very stepwise linear discoveries where we just build on our old knowledge and build. The reality of the situation is that sometimes in science, we got to take 3 steps backwards. A lot of times we do incrementally build, but sometimes we realize that one of those steps that we took a long time ago was completely wrong. And so the Nobel Prize system doesn't really have a good way of dealing with that, because something could appear very brilliant and then turn out to be completely wrong. And I'm not aware of that having happened in any other case other than the CMB business. And there's something particularly hasty about the way that the CMB was done. You know, like I mentioned to you guys, it was reported, literally the curve of what the guys measured for the first time was reported, and the subsequent paper in the same journal was the Nobel Prize winners who said this is the echo of the Big Bang. That's crazy. So generally speaking, when people observe something nuts in nature, they write about it. People go back to their laboratories and think about it for a few years. A bunch of papers come out trying to explain the phenomenon that's weird. And then eventually, you know, maybe the scientific community comes to a consensus, maybe not. And that's kind of where you would think people would start handing out prizes. But no, it happened very, very, very quickly. And so I think if there's a lesson in there for the Nobel Prize Committee, it will be not to be in such a hurry to come to conclusions about stuff. It's a weird situation, though. It's very weird. Nobel Prizes, you know, again, in science, the only thing you have is your name as a scientist. You don't get big sums of money for coming up with brilliant ideas. Maybe if you quit science and go and work for an engineering project, you know, building whatever, computers or something, you might make a lot of money, but you don't really have the incentive of money in science. It's all just reputation. So these prizes are extremely important to scientists. And yeah, I don't know how we walk back on making mistakes on this, although I think we're going to find out really soon. But my guess is that Penzias, Wilson, Smoot, they will all be dead before any of these paradigms collapse completely, as I'm predicting that they will. All right. Any other thoughts, guys? Yeah, Levin. Oh yeah. Did that happen already? Tonight? All right, total lunar eclipse, guys. What did we say? Like 11 o'clock or something? What's that? 10:30? Somewhere tonight, before midnight. Go check it out. It should be really cool. If the clouds get out of the way, that is. It would be very pretty. Should be kind of a reddening and a darkening of the moon, very transiently. Yeah, that's cool. Go check it out. All right, let's. I do want to go back a little bit and talk about this diagram a little bit, because I want to make sure I think we maybe confused this a little bit, and I want to be very clear about what's going on here. So the idea is that with this diagram, this is with our discussion of the ocean hypothesis of the CMB. The idea with this diagram is that there's these weather satellites they use to measure the temperature of the ocean, which is where a lot of this data comes from. And what they do is they realize that in order to get an even halfway correct measurement of the temperature of the ocean, they actually have to point the thing slightly off axis. So this is a chart that shows the angle at which they're pointing the antenna from the satellite as they're looking at the ocean. Now they know the actual temperature of the ocean because they got all sorts of other sensors. They got ocean buoys, they got ships, they got all sorts of ways of measuring the ocean temperature. So they know where the temperature is accurate. And they're basically using that simple relationship between luminosity and the fourth power of temperature in order to arrive at this temperature readout with light, right? So they're not necessarily looking at a black body temperature with this, but they are looking at the power of the light over some given surface area, and they're deducing the temperature as a result of it. Now, what's interesting about this is that when they calibrate these satellites, they actually have to point these things at the limb of the Earth in order to view the CMB. And that makes sense in some way of thinking, because as you can see, the temperature at 90 degrees completely falls to zero using this readout of luminosity. So the theory here is something like this. And actually, my wife, Anastasia, made this beautiful picture for us. Actually, the next 3 slides I'm going to show you, she made these because I think they sort of show what's going on here a little bit better. The theory is something like this. There's actually 2 different ways that water molecules can vibrate. One, and perhaps the strongest way that waters vibrate, is really well known. So waters are basically these kind of bent-looking molecules. They got 2 hydrogens stuck onto an oxygen. That hydrogen-oxygen bond vibrates like this. This is called the OH bond. And you can kind of see that over here on the left-hand side for you guys. It's kind of coming out of the page. So there's a vibration there that's really strong, this OH bond. Now, there's another bond possible as well, which isn't usually discussed, which is the hydrogen bonding of the water. This is kind of a transient bond that forms between the hydrogens of one water molecule and the oxygen of another. This is what we're saying that the lattice of the ocean is comprised of. It's a very transient hexagonal lattice that's created under the giant compressive weight of the ocean, by which there's actual layers of water. It has short-range order that results from the hydrogen bond network. It is, in some sense, very quiet compared to the loud OH bond network. So what we think is happening here is that these long arrows that you're seeing are the radiation from this previous curve. They are the OH vibration signal of the light that's coming off of the water. It's emissions in the OH, from the OH bond vibrations. What's interesting, though, is that those OH bond vibrations are very directional. So the length of the arrows here corresponds to how intense that radiation is that's coming from the OH bond. So as you can see, as it gets down close to the horizon, it gets really, really strong, actually. But then it completely drops to zero beyond, let's say, 80, 85 degrees from, the normal, from the zenith of the instrument. However, black body radiation's different. It's very, very different in that black body radiation has no directional preference. It shines in all directions all the time. In other words, it's not polarized. So what we think is happening is that this hydrogen bonding network is the source of the black body radiation from the oceans. And what it's doing is you can see those little tiny dotted arrows represent the black body radiation, which is the same in all directions. And it continues to shine down below where the other radiation falls off, where the OH bonding radiation falls off. Which means that when you take your satellite and you look off at the limb of the Earth, you're kind of looking underneath that OH bonding. So you lose that really big, strong signal that you're measuring the ocean temperatures with, and you're starting to get a glimpse of the hydrogen bonding temperature of the black body of the oceans, which reads out around 2.7 Kelvin. So this is, again, it's very hard to understand this because when you measure a black body temperature, the only time you get the actual temperature is if there's no other processes happening. No convection, no currents, no other ways that that energy could be dissipated. So all of the black body work was done in these soot-covered chambers that are where you put something hot inside of it and wait for it to come to thermal equilibrium with the soot-covered chamber, and you measure the light from it. And then you get a true readout. But if you use any solid or liquid body that has convection currents in it, like an ocean would or anything like that, you lose a lot of the heat to those other processes, right? So in the ocean, most of the temperature is tied up in the actual motion of the water molecules. It's tied up also in energy going into the vibrations of the molecules themselves. The residual temperature from the lattice itself gives you a black body temperature of 2.7 Kelvin, but that's a very small contribution to the overall temperature of the system. This is why when we look at the surface of the sun, if you guys think back to the beginning of this class, we said, man, it's kind of weird how when we measure the black body temperature of the surface of the sun, it's only 5,700 Kelvin, but the atmosphere is at, 10 million Kelvin. How is that possible that the air inside the oven is orders of magnitude hotter than the oven walls themselves? It's very perplexing. And so we talked about different ways that average kinetic energy of the particles could give a misleading idea about how hot the atmosphere is. That's true. Another piece that's true is that the surface of the sun clearly has convection currents on it, right? We've seen those little bubbles, those kerneling at the surface of the sun. So a lot of the heat is tied up in things other than the black body radiation. That means that the temperature that we're getting off of the surface of the sun can't possibly be an accurate temperature for the surface of the sun. It's probably far hotter than 5,700 Kelvin, just like the ocean is far hotter than 2.7 Kelvin, because the black body radiation is only a small contributor to the overall heat balance of the substance itself. Okay, so I hope that clarifies this system. Nastia made another picture here, which is another way of thinking about it, which is that at each angle that you're looking at the light from the satellites, the white arrows are from the OH bond, and that they're dominating at these more normal angles. But as you get off to the horizon, the red arrows, the black body, persists where the OH light actually falls off very, very precipitously. And so all you're left with at the horizon is the black body radiation itself. So that's the story. That sort of, I hope, clarifies the picture with respect to the satellite measurements of the temperatures coming off the ocean. Questions about that before I move on? Yes?
How does this relate to the antenna being 90 degrees?
So if you go back to the antenna looking directly down, right? If it's looking directly down from above, it gets a pretty strong signal from the OH bonding. That's the straight arrows, basically. This is a thermal temperature from this vibration of the molecules, right? But And this is the same picture, but just from a different angle. But if basically, if you turn that thing off axis, if you turn the satellite off axis, so I guess the satellite didn't have to be turned in this case. We could just imagine the telescope still looking straight down. It's going to not be able to read any radiation from that OH bonding at 90 degrees. And the first radiation it picks up on these long arrows is going to be at something like 80 degrees from its central point. If it's looking straight down at the ocean, it'll be around 80 degrees. And the most intense radiation it gets is between, let's say, 70 and 80. If we go back to this figure that shows its actual intensity readout, it's pretty close to 80 degrees, and then it drops to 0, basically. So the reason for that, in some sense, the reason that at that point, what you're left with is a residual temperature is because, well, in theory, is because the black body is not polarized. It's in every direction uniformly. Black bodies are always emitting uniformly in all directions. It's never polarized light. Whereas the OH bond is a polarized kind of light. It means it's emitted preferentially in different directions. So it basically sneaks in underneath the polarization window of the OH bonding. It's very complex, guys. I'm doing my best to explain this to you, but it's a very technical argument, unfortunately. I would say, like I say, for me personally, the strongest argument in favor of this ocean hypothesis is how beautifully tight the error bars are on that CMB measurement close to Earth, and how hazy and awful they are when we get farther away from Earth. They don't seem to get better, which is weird because you would think that when we're further away in space, if we're measuring a cosmic source, we would get better readouts the further we got away, and that does not seem to be the case. I can also make an argument on first principles, which is really strong for me personally, which is something like gases never, ever give black body spectra, ever, in a laboratory. We've never, ever seen anything even sort of approximating that. And the entire story of where this CMB comes from under the Big Bang cosmology is that it comes from these photons at the beginning of time that are from some sort of like primordial gas that doesn't even involve atoms. It's this like primordial soup. And so the question becomes, can you get a black body spectrum from something that doesn't have a lattice, that doesn't have at least a transient lattice like water, or a real firm lattice like a solid material like the black body chambers that were used for all of the work originally? And it doesn't seem like you can in a laboratory or anywhere else that we've ever looked. The only place that anyone will ever say that we've seen a gas or anything other than a solid or liquid give a black body is they'll point to stars. And they'll say, well, the stars are gaseous, so we know that gases can give black bodies. But that's a very circular argument. So, technical arguments aside, I think on first principles, it's a very difficult argument to be persuaded by, at least for me. Questions? Thoughts? All right. So let's try to, with the last half hour or so here. Yeah, Lemon.
So if the antenna is pointing straight up and the ocean's like off to the side, then how does the light get in?
Well, the idea is that there's leakage since the black body radiation is completely isotropic. It's in all directions. That there's leakage over the edge of the horns, basically. And so there's a technical argument to be made about how susceptible those horns are to spillage from the sides. And it seems like they're pretty leaky, but that would require a whole nother argument. There's some work on that done, though, which is worth checking out. I can send you a paper later, actually, if you remind me. But yeah, it seems like they're leaky. All right.
Has water ever been measured in a lab? Like the black body of the water?
That's a really good question. The argument is that in order to get a big enough lattice to make a radio signal in the microwave, you would need a huge body of water to do it with. And so the only way that you could measure that is the way that it's been measured in these experiments that we just got done talking about. So the argument would be that it has been measured, and it's measured when they calibrate the CMB at the limb of the Earth. That's what they're measuring. You couldn't do it with a glass of water, for instance. It wouldn't have a big enough lattice to give you radio signals, essentially. You'd be able to get that OH bonding, but it wouldn't be a black body curve. It would just be these OH emissions, essentially. So there's a lot of moving pieces here. You know, it's very strange. It's very strange to call a radio signal coming off of a substance a black body, to use black body equations to derive the temperature when you know it's not a black body. But we do make that exception in the generalized form of the Stefan-Boltzmann equation, which is that equation that says luminosity is directly related to temperature to the fourth power. Try to apply that to substances in general. We know it doesn't give us a real temperature, but it is proportional to the real temperature in some sense. So that's why, depending on where you point this thing and how you're picking up polarized light, you get different temperatures as a result of it. There's a lot of factors that go into that because it's not a true black body temperature. It's just the luminosity that's being assigned to temperature through this Stefan-Boltzmann relationship. Ugly technical stuff. I'm sorry, guys, but it is the case. But yeah, Levin, if you're interested, I'm happy to send you a paper about the design of those antennae and the leakage across the horn. It's very interesting. It certainly opens up the possibility of what everything I'm telling you here is the case. Again, I could be totally wrong. I just find it to be a really interesting explanation that's different from the one that you're probably going to read in your textbook, which is really what I want you guys to be exposed to. There's always an argument going on behind the scenes, and I think that's what's really cool here about this whole story. So, you know, I also want to, hopefully in the next half hour, I want to try to work out this problem of why in the world we have such a fantastical cosmology today. And by fantastical, what I mean is a cosmology where we're okay with, first of all, we're okay with hearing a story from physicists about how physics breaks down sometimes. In other words, it seems really shocking to me that the physicists of all people, although I might argue that they're more mathematicians than physicists, but the mathematicians working on these physical problems would come up with answers that essentially amount to physics breaks sometimes. I really want to try to figure out how that happened. There's also, and there's a background to that, which has to do with the stories that cultures tell about themselves across time. And generally speaking, the cosmologies that people have talked about across time, they are mythological in scope. And generally, I'm going to make the arguments, whether it's the Christian tradition or the Babylonians, the Sumerians, or the Egyptians, or the Mesoamericans, the cosmologies generally involve some sort of war between two opposing forces. And those two opposing forces are usually something like order and chaos. And I'm going to make the argument for you guys that there's not a situation in which you want either one of those two forces to win completely. So we've had societies on Earth where that have been overly ordered. So an overly ordered society might be something like it could be on the right wing or it could be on the left wing, honestly. So there's really left approaches to that and there's right approaches to it. So there's these kind of utopian visions where if we overly structure things, say in the case of like a fascist government like Nazi Germany, right? We have all these constraints on how things should be. We end up with a horribly repressive and tyrannical government that is murdering people willy-nilly because it wants to clean up its population and reorder things. And it's going to force that to happen under violent extremes. The same thing could happen in a left-leaning government that's gone completely overboard. So, you know, the Soviet Union, Mao's China are great examples of that, where you have this centrally planned, this central planning, almost a scientific approach to the management of people and resources. Again, an attempt to sort of overstructure things. These people should get these resources, these people should get that. Again, it completely fails because it's an impossibly complex system and economy, and you know, millions of people end up dying in either case. And that seems to be a theme that holds up all throughout history. Whenever these states become too structured, they become very tyrannical. Obviously, if the state doesn't have any structure, then you have a bit of anarchy, and that's a disaster as well. There's also a factor that's playing out right now with respect to the cosmology that we don't have in the mythological space. So if you guys think about what are the stories that we generally tend to tell about the future in our mythological landscapes, which I would submit to you are probably mostly Netflix, Hollywood, stuff like that, right? They're mostly pretty bleak pictures of the future, right? Most of the stories we tell, like how many stories do you guys know about the future that are really rosy and tell this beautiful vision of how we're going to solve all of our problems and we're going to sail off into the sunset and everything's going to be all right? Almost none right now, which is really interesting. I think it's kind of indicative of something. And I would actually submit to you that the story that the physicists or the mathematicians or whoever's in charge of this cosmology business right now, the stories they tell are also equally apocalyptic. Because how do they explain what's happening right now? Well, all the objects are drifting apart from each other at light speeds, essentially, especially as time progresses. Eventually, all of the galaxies, all the stars are going to burn out, they're going to drift impossibly far away from one another, and the universe is just going to kind of terminate in this like cold heat death of everything. And it's very dark and apocalyptic in some sense. I would say even the fact that, I skipped over that first slide, but 96% of the universe is supposed to be made out of dark stuff, like literal dark stuff. Like it is such a grim picture. Even in the symbolic language that we use, dark matter and dark energy. We can't see this stuff, but we know it's doing stuff. It's kind of this unwieldy shadow force behind everything. So there's something really apocalyptic about the way that we view our own future in a mythological context and also in the physical cosmology space as well. And I would argue that reflects more about our own trepidation about the state of our civilization than it does anything else. I would say that we're very, very worried. I saw some incredible survey the other day of young people who were like, I think 200 years ago, young people were probably worried about how to get their own farm started, probably how to get married, and how they were going to, have as many children as possible to work their farm. Today, young people are worried about stuff like climate change and overpopulation and whether they're going to be able to get a job or not, or it's going to be replaced by AI, something like that. We have these like really apocalyptic fears that are very unique to our present point in time that I think human history has not really had to wrestle with in the past to the extent that we are dealing with. And so that's kind of the backdrop of the cosmology that we've thrown up the flagpole at this point in time. And I think that's worth keeping in mind as we work our way through this. So what do I want to say about this? The mythological overtone of the present Big Bang cosmology. Antonio mentioned that he kind of liked the Big Bang because he embraces a Christian mythology, let's say. And I don't mean to say that that your story is mythological and that it's wrong or not real. I actually think myths oftentimes encapsulate reality better than anything else, certainly better than equations or anything like that. The story that's behind the Big Bang of this birth of everything is not a new story. We can start at the present moment and work our way backwards, but what we'll see is that who was the first person to assign the redshift to a birth of the universe? Well, it was a Belgian priest named Lemaitre, right? And Lemaitre didn't come up with that on his own. He, of course, read it in the Hebrew Bible and the tradition of this creation moment, right? And he just found a way to map the data of what was happening onto that story. But if you go back even past the Hebrew tradition, right? Who were the Hebrews? Well, they were a particular clan of people who were coming out of this bigger culture called the Canaanite culture. And the Canaanite culture, in some sense, was a Semitic culture, much like the Akkadian culture that predated it and sort of overlapped with it to some extent, who really were the ones who colonized Sumeria, which was kind of the first civilization in the West. And so when they took over Sumeria, they created this empire called the Babylonian Empire. And so this story, this creation myth in the Christian Bible, in the Hebrew Bible, it can really be traced all the way back to the Babylonian, let's say, creation myth, which has a lot of similarities. In particular, the flood story first appears. That's the first time we get this kind of Noah's Ark story, is in the Babylonian creation myth. But in any of these cases, they all share some similarities, right? And they all talk about this. By the way, this isn't just related to the Sumerians. We'll find this in every other culture, something very similar all around the world. And I'll walk through those in a second. But we all have this moment where the universe begins in all of these cases. And oftentimes it's hatched out of an egg of some sort, which is very similar to the Big Bang story. And it oftentimes gives rise to the vision of the world as it's apparent and observable for everybody under it. So, let's talk a little bit. I want to just tell you guys a little bit about the Babylonian creation myth a little bit, because it's kind of interesting. And I think that there's some real gold in it as far as the wisdom of what it means to organize a society. And I think all these creation myths contain a lot of gold too, by the way. I think they are not just silly, superstitious stories. I think they encode a great deal of wisdom, which is, I think, really the purpose of these creation stories ultimately. So in this case, the world is kind of created, and we'll talk about the creation moment in just a second. But it's basically divided. They set up the world with this really interesting representation. It's you of course have the sky, you have the earth, and then you have this watery world, the underworld, right? Which is very salty. And what happens in the very beginning of time is that the salt and fresh water are represented by these two deities. One's called Apsu and one's called Tiamat. And Tiamat's kind of this serpent deity, and they're kind of locked in this embrace together. They're sort of wrestling. And this, in some sense, I think represents this idealistic union of opposites, right? There's something generative about it. The sort of mother and father, however you want to see it. There's this yin-yang too. And we see this in many, many cultures. So this embrace, in a generative fashion, almost procreatively, gives rise to the first gods. Now, the gods are interesting in all of these societies. It's most evident in the Greek traditions, which descended from all of this many, many years later, thousands of years later, that the gods, in some sense, each represent some aspect of those passions that live within us, right? So we have the gods of lust, the gods of rage, the gods of inspiration. There's all these aspects of these experiences that we all have, that we know how to have without anybody teaching us how to have them. I think that's the most charitable interpretation of what these gods really meant to these people. It's sort of like today, we would talk about these in psychological terms, right? Because we try to sort of medicalize it. We try to sort of turn it into a scientific matter. But the fact of the matter is, no one ever had to tell me how to be angry. I know how to be angry. When I was when I was 1 day old, I knew how to be pissed off, right? There's things inside of you that you know how to do without anybody explaining. And I think that's really what the gods represent, because the stories that are told are, generally speaking, how to negotiate between these different passions that live within you. And in some sense, as we get this sense, this real vision of ourselves that emerges, right, in early childhood, we start to be able to consider ourselves as an independent entity. And all of the people that you meet are also independent entities. And we all have to sort of subsume these passions and get them under control and make them work for us as a totally integrated human being. And I actually think that our whole job across the course of our lifetimes is really to integrate all of those things, right? It's probably the hardest thing in the world to do, is to take complete control over all of those subconscious programs that are trying to run amok with yourself, right? And I think a lot of these spiritual movements that people have tapped into and have gained a lot of popularity lately, like meditation, yoga, basically all sorts of alternative spiritual practices are really aimed at being able to take a step back from your passions and be able to get a hold of yourself as a whole. I think that the Sumerians and the ancient indigenous traditions we'll look at, I think that they were largely talking about the same processes. They just happened to embody each one of those passions with the name of a god of some sort. So, okay, anyways. What happens is that these primordial two beings, whatever they are, these gods, they sort of copulate and give rise to all these passions, all these individual gods. Those passions, those gods actually end up killing the father deity, Apsu, which is really interesting. So they sort of destroy him, which I could read as like a sort of symbol of like a sort of rebellion against this patriarchal order, right? I talked to you at the beginning about when cultures get over-ordered, right? Nazi Germany, Maoist China, Soviet Russia. I'm going to stay away from the present era, but like the point is, when things get over-ordered, they become tyrannical, and oftentimes people rebel against those, and they'll kill off the sort of tyrants at the heart of that. And this is a common story in every single culture. And I think that the Sumerians encoded that in their creation mythology. So Tiamat, she's the female deity of the two at the beginning. She gets really pissed that the sub-gods had killed off her consort. And she sends a flood, actually, to wipe them out, which is quite interesting. Right. Now, there might be actual historical basis for this flood business in people's memory, because you got to keep in mind, this civilization appeared a few thousand years after the end of the last ice age, last glaciation, to be more technically proper about it. When those glaciers melted, 10,000-ish, 10,000 BC, something along those lines, the sea levels abruptly rose over the next few thousand years by as much as 300 feet. So think about where all of our biggest cities are on Earth right now.
This is like directly correlated because of the timeline, but near the beginning of this class, we talked about, I forget what scientist was looking into it, but like how, since water is a really good absorber of sunlight, that there potentially could have been a lot of excess water or extra water within our atmosphere. Could there have been like some situation where that water would then like rain a lot, or it would collapse, and that not be cause of like a flood documented across different cultures that are like around the world and then brought into different mythologies?
It's not even controversial, 100%. So absolutely, the climate changed abruptly. So there's a lot of feedback mechanisms there, right? So if the temperature of the Earth goes beyond a certain point, the glaciers melt, the polar ice caps melt. And that's actually happened right now. We're in one of those warm periods. This is very predictable over time. We're constantly oscillating between these really warm and really cool periods. When the glaciers melt, they stop reflecting the sunlight back as much. So you actually have more sunlight coming into the Earth on balance in general. So it's kind of an amplification. You also have all that water injected into the atmosphere, right? So that made for an incredibly fertile period a few thousand years later, too, where there's all these rains, all of these places that were formerly, kind of arid began to actually have all of this flooding, all this fresh water melting off of the different mountain glaciers and so forth. So you saw places like this, what we call the cradle of civilization in Mesopotamia, where these river valleys become incredibly fertile all of a sudden, right? And they can sustain these huge agricultural projects that give rise to the first states. Mesopotamia, Indus Valley in India, the Yellow River Valley in China, the same thing's happening. This is all kind of happening at the same time. Like, it's really bizarre because the first civilizations kind of all appear at the same time, more or less. It's not like somebody figured it out and went and told everybody else. Like, everybody kind of like arrives at this moment together, as far as we can tell. Now, there might have been civilizations that we have no record of. Certainly that's a popular idea in some circles too, maybe. But my point is that something, not only did the force that gave rise to all this fertile land, not only was that wonderful for the advent of agriculture, it was probably also really disastrous for the people who were hunter-gatherers and shepherds and people who were living in small city-like congregations, because where are all of our cities today? Like, where's the biggest cities? New York City, Los Angeles, San Francisco, Vancouver, Seattle, they're all on the ocean. They're all on the ocean. And if the ocean's not going to rise 300 feet because we're already at a maximum right now. But like if the ocean, if you had dwellings, people like living on the water, right? So if the ocean rose 300 feet today, all those cities would be underwater. They would be gone. And the ocean destroys everything. Like there would be almost no trace of anything left, right? So something, I'm going to make the assumption, again, assumptions are everything in science, right? But I'm going to make the assumption that people back then also liked living near the ocean because it's a great place to live. You got tons of food, right? You can just throw some nets out, get dinner. It's a wonderful place. You can travel really easily on the ocean. You can just get in a boat and go hundreds of miles this way or that way. Trade is facilitated. Living on the ocean rocks. And I think that it always rocked for human beings. And I think that it's very likely that most people were living near the ocean since ever. The oldest, if we look for the bones of the oldest human beings, like anatomically modern human beings, where do you think they find those bones at? They're all in caves right by the ocean, right? So I think humans have always lived by the ocean. And I think that when the sea levels rose abruptly over a couple thousand years, there was catastrophic flooding everywhere for various reasons. There was literal dams made out of glaciers that were housing freshwater lakes that just melted. Huge amounts of water were let loose. The entire region, for instance, between England and what we would call the English Channel today, I want to say as recently as 6,000 BC was completely devoid of water. It was it was called Doggerland, and there was they've done some archaeological underwater archaeology there and found all sorts of settlements and structures and the remains of structures, henges and all of that stuff. So something terrible happened for sure. I think the introduction of this flood into these creation stories is not without some nod to some historical disasters that happened. But there's also a sort of sermonizing or a moralizing about it too, right? Because what happens in this story is that the god becomes angry that the sub-gods did away with her order-giving patriarchal consort, right? And so in some sense, the flood is interpreted as this revenge act for basically doing away with this order-giving side of nature, right? It's kind of, and if you read the Hebrew Bible or the Christian Bible, for instance, there's kind of this overtone in the Noah's Ark story, which is kind of if you don't have your stuff, if you don't have all your, Noah's told to basically go and build this ark. And in some sense, I can interpret that as being being prepared for whatever eventuality may come, right? Sort of this act of getting your life in order in some sense, getting your things together, right? He was I'm going to build, I feel like there's a flood coming. God tells me there's this flood coming. I'm going to build this ark so that I can survive the flood, basically, right? I think that same sort of story is playing out here because, the next story about what happens is that all of these gods kind of hear that Tiamat's pissed off and she's going to come and kill them. And so they basically concoct this savior king named Marduk to basically organize the human beings into a functional unit such that they can kind of weather the chaos that Tiamat's going to unleash in the future. So they can weather the floods of the future, something like that as well. And what's interesting about this savior Marduk character, and I personally think there's a lot of similarities between the Marduk character and the Jesus character of the Hebrew Bible, or the Manu character of the Persian mythology. You kind of see this kind of savior character pop up over and over again. But Marduk's really interesting because Marduk has the unique power of speech, right? He seems to be the first time that the humans have somebody who can talk for the first time. He also seems to be characterized by incredible vision, so he's got eyes all over his head, basically. And I think that's a really interesting representation of what you would want out of a king, actually, or out of a leader, let's say. You want somebody who can communicate really well, and you want somebody who can see what's happening really well, right? And so in the Babylonian tradition, all of the kings are actually named Marduk going forward. So they may have different last names, right? They have different surnames, but their first name is King, is Marduk, King, Marduk, blah, blah, blah. And so in some sense, they hold their rulers up to this really high standard going forward. And that's something that's very strange that we don't do today. I think we all probably at this point expect politicians to be liars and cheaters and womanizers and everything else, right? It's just kind of like the standard. I think that was completely anathema to these cultures originally when they were setting up these states. I think they realized that if their leaders weren't held to the highest standard, then Tiamat would come and knock them down with a flood or whatever it was. And there's something to that. There's something to that need for order in order to ballast yourself against what comes. A really good example of that in modern times is the dichotomy between what happened in the wake of 2 earthquakes that were very recent. Did I write down the dates of these? So there was a big earthquake in LA, and there was a big earthquake in Haiti. I don't know if you guys are too young for all of this, but this was maybe 10, 20 years ago. And they were approximately the same magnitude of earthquake. So the earthquake in LA was, I think, 7. I think the one in Haiti was like a 6.9. Oh, okay, here we go. I wrote it down. The Haiti earthquake was actually a 7, and the LA earthquake was a 6.7. These were basically happened around the same time, but they had very different outcomes. So the earthquake in LA killed 57 people, which sucks. That's a lot of people to die in an earthquake. It's horrible, for sure. The earthquake in Haiti killed 200,000 people. What's the difference between LA and Haiti? Well,
I was going to ask, Haiti probably has different style buildings. I'm sure people are more squished together.
yeah, I mean, the difference is the history of Haiti is a complete nightmare. So Haiti was founded as a slave colony, first of all. And it's actually one of the only stories of a successful slave rebellion that ever happened. Basically, the Haitians threw out their French overlords who had enslaved them, and they set up their own country. Now, as you can imagine, the colonial empires for the next 300 years did not take that very well. And so Haiti has an incredibly tragic history of being cut off from all of the necessary trade arrangements, agreements, infrastructural pipelines that would be necessary to build a really robust city like LA, for instance, right? So LA, California, it said, could basically be its own country. It's such a wealthy place, unbelievable intellectual property rights, for instance. They have Hollywood there. They have a lot of the tech industry in California. Hollywood's really rich, let's put it that way. So the result of that is that for the first part of its history, it was a really well-managed state. California used to be amazing, by the way. Not to put it down too much right now, but they had for most of the 20th century, they had a public education system that rivaled the Ivy League education system. The California system was incredible. They had public transit systems that were way better than anything on the East Coast. Basically, California was an amazing place for most of the 20th century. A lot of that slipped in recent years, but that's a different conversation. My point is that preparedness and let's say ordering your society in the face of what will come can go a long way. So natural disasters are a nightmare, but if your civilization is ravaged by pillaging and corruption, assassinations, Haiti's basically never been able to establish a solid, robust government after all these years because it's just been really hobbled by its colonial past to the point that it's just never really had a chance to build a stable state, let's say. So there's something to that. Nature will definitely come knocking and it will do horrible things, but what comes from that largely has to do with how your society has prepared for that future. Sometimes that's out of your control in the case of Haiti. I don't mean to blame it on the Haitians. I think that they were really, really disadvantaged by the colonial superpowers of the day, all the way up to the present, honestly. Okay, so in some sense, I think this cosmological story, this creation story from the Sumerians, and we can trace it all the way through the Western tradition. I could have picked on the Greeks. I could have picked on the Hebrew Bible. And in some sense, I think is a really cool story. And I don't, that might not even be the best way to put it. I think it's an incredibly wise story that encodes layer upon layer of information about how to structure your civilization in a way that will result in the best possible future. And that was the goal of cosmology in the past. That was really what people were trying to do with these stories that they told about the universe. Who are we in relationship to the forces of nature that will impact us going forward? So, I kind of ran out of time telling the story across other cultures, but needless to say, we see the same thing in almost every other culture around the world. There's almost always two deities. And this is in the case of the Mesopotamians. Same thing happens in ancient Egypt. You have these warring personalities of chaos and order that are always trying to fight it out. And what is the ideal balance between chaos and order? An overly ordered civilization is a nightmare. An overly liberal society that just has all 100% freedoms and there's no structure to it whatsoever, that's also a nightmare, right? So it's our job, in some sense, as citizens of the world to orient ourselves towards the proper balance of that going forwards. And we do it in our own lives, as I've pointed out, as we get older and we mature and we learn how to bring all of our different passions under some banner that we call ourself, where we're actually able to make decisions and do things without just crying like babies. And, in some sense, this argument between the eternal universe, like I said, the steady state cosmology, and the Big Bang universe, they sort of sidestep any of these cosmological questions, right? In some sense, by making cosmology an entirely physical story, we've really abandoned even the necessity to examine these kind of questions on balance. In the final analysis, half of what's happening in this classroom is not physical. I think we would all agree about that. There's things that are happening that are metaphysical. They're beyond physics. Yeah, we all have bodies that are made out of atoms. But, even your body is going to be made out of different atoms 10 years from now than it is today, right? The atoms are only half the story. So the way that I like to see this is kind of like we have two eyes for a reason, right? If you go all the way back to the beginning of this course, we were talking about parallax, right? We get depth perception because we have two eyes, right? I think cosmologically, and the way that we approach understanding nature should also probably be done with two different eyes. One of those eyes is physical, right? There's absolutely a physical story for what's happening. I've tried to give you the most physical explanation for what I think the stars are doing that I could have possibly stumbled into in all my years of studying this. That's kind of been half of this course. The other half of this course, hopefully, has been about the other side of things as well, the mythological side of things, this orientation towards a wisdom about how we actually project ourselves into the future. And personally, I don't see how we can get on to a better future than the one we have today if the only way we look at our relationship to the universe is physical. That seems kind of preposterous to me. In other words, if we ask the physicists to explain the universe to us, they're going to inevitably fail. We're going to end up with preposterous monster entities like dark matter, dark energy, black holes, world-swallowing physical breaks in the space-time continuum, right? Because physics is unprepared to actually answer questions about meaning and about wisdom and about how to actually act in the world. I think that, again, that's only one eye. And if we're only looking at the universe through one eye, which is this physical lens, we're going to end up not only with some crazy stories, but we're going to perhaps sideline a lot of the stories that we should be telling in the background. So, how do I want to put a bow on this exactly? Cosmology is kind of this endeavor of putting together a map, right? And we each have to do that, I think, as we go out into the world. And I hope each one of you will continue to create better and better maps for yourselves about your own lives and how you can improve your relationships to everything around you, the people around you, and to the future itself. And I think that we should be creating, right? I asked you guys to do creativity projects for extra credit in this class. I think that through those creative processes, and everybody has them, I don't know whether you do painting, you write poems, you cook, you do whatever you do, you're actually imagining, right? You're imagining a future, say you're cooking for friends at dinner, you're actually creating a future that's better than the past for those people that are coming to that dinner. You make a painting, you're doing it because you want to transcend ordinary reality and give a better future than the one that came before. And so, anyways, I urge you guys as you go forward into your lives in the future to think about cosmology not just merely as this physical battle of what the stars are doing in their atomic form and so forth. Although I hope you guys will pay attention to that as it unfolds, because I think there's going to be some really fun, interesting headlines coming out in the next decade or so. And I hope you guys will remember back onto this class as that unfolds. But I want you guys to also think about your own contribution to the cosmological mythos of our society. And think about, maybe some of you will go on and do great works. Maybe some of you will be filmmakers, or some of you will be teachers. Think about putting forward that mythological future that isn't just a bunch of zombies starving to death at the end of capitalism, right? There's a better world, but we have to literally make that world happen, each one of us. We have to imagine it first. We have to see that. We have to have that full vision using both of our eyes in order to pull that off. So I will rest my case at this point. It's been really fun to have you guys in the class this semester. I'm a little bit sad that it's over, but I hope you guys have a wonderful rest of your semester. Good luck with finals. And pop your head in and say hi next year. It's always good to see where people end up. But take care, guys.